Hello everybody and welcome to Chapter 4. In Chapter 4 we'll be talking about Riemann sums and definite integrals. So really in Chapter 3 we learned about indefinite integral. We saw how to compute it, but we didn't really have any important application for it. We saw a small one of finding antiderivatives with specific conditions, but what we're after is a really important geometric application. So what we'll do in this chapter is we're going to start with a problem of finding the area of a region. We'll construct a way of getting the area of the region, and in section 4.2, we're going to link it back to the integrals of chapter 3, and then we'll see how to compute them using the techniques that we've learned in chapter 3 as well. All right, but at first, we'll start talking about the area and trying to find a systematic way of computing the area of a complicated region. Good. All right, so let's get started. All right, so we're going to start with Riemann sums, and our goal, like we said, is to find a systematic approximation for the area of complicated regions. All right, so let's do in section 4.1.1, we'll look at just one problem and see how it gets us started. All right, so in this section, we approximate the area of geometric regions using rectangles. To get approximation that are closer to the one, we'll increase the number of rectangles that we use. So let's start with a classic problem. Find an approximation for the area of a disk of radius 1 using one rectangle. All right, so I'm not going to get an exact answer doing this, but I am going to get an approximation. So what I'll do is I'll cover this region with one, well, whoops, this is not a great rectangle. All right, we're going to cover it with one rectangle. And so I want to know what's the area of this region here, and that's going to be my approximation for the area of a circle. So area of the disk is not equal, somewhat close to the area of the square. All right, so let's see. This is a circle of radius 1, so this point is 1, 0. This point is minus 1, 0. So really, the width of the square is the diameter, which is 2. All right, same thing. The height of the square is the diameter, which is 2. And so this area is base times height, which is 4. All right, so we know the real area of a disk. It's actually pi r squared. So in this case, it's just pi. So what we're getting here is that pi is approximately 4. Of course, it's 3 point something, but that's not too far. Like we're not 20 times the size, right? We're just a bit over because we're including all of these extra bits here. And so these add up to getting 4 instead of pi. If we want to get something closer to the real area of a disk, what we could do is instead of using one rectangle, which is quite crude, we could use 4. So let's try this. What I'm going to do is I'm going to divide my axis into 4 different sections. And for each, I'm going to build one rectangle. I'm going to take it so it covers, just because I think that looks nice. So this one will be a bit taller, and then again one tall one, and then one a bit shorter. All right, so I'm going to get 4 different regions, 4 different rectangles, and I'm going to say that my area is approximately the sum of all of these. Let me Move it slightly left so I can complete what I wanted to write. All right, so I'm going to add the area of the red, the area of the orange rectangle, the area of the blue, and the area of the green, right? And that's going to give me a better approximation, better because I'm not adding as much as I was adding here, right? I'm saving a bit of spot. So I need to figure out the base and the height of each of this. I mean, the base is not too bad because of the way we constructed them, they're all equal length, so they have length 1/2. Because I divided an interval of length 2 into 4 little pieces. Now I need to figure out let's figure out what this point is. We're on the trig circle. We're on the circle x squared plus y squared equals 1. So the x component is 1/2. And then if you want to get the y, well, you could use trig circle. So this is cosine of pi on 3. I'm going to get root 3 on 2. Or you could just solve for y in this, right? So if x is 1/2, then y is plus or minus root of 1 minus 1/2 squared. And I get plus or minus root of 3/4. And so root 3 on 2. So this one would be with minus root 3 on 2. The one on top is plus root 3 on 2. And so what I'm getting here is that this height is, well, root 3 on 2 minus root 3 on 2. So really I'm getting root 3. Same thing on this side. I'm getting root 3. And then the middle is going all the way to this point, which is 0, 1. 0 minus 1. And so this height here is 2 again. All right, so let's write this all down. So the area of disk is approximately, the area of the green is this height, which is root of 3, this width, which is 1/2. So it's root of 3 times 1/2. The area of the blue, that was 1/2. This is 2, so I get 2 times 1/2, but really height times base. Then 2 times 1/2 for the orange, and then root 3 times 1/2 for the red. So all in all, if I put it all together, I get that the area of a disk is approximately root 3 plus 2. And so if I actually compute this, I'll get about 3.73. So I'm getting a better approximation. Not perfect, but if we keep increasing the number of rectangles, we'll get a better and better approximation.